Hello everyone, welcome to our second video. In this video, we look at the augmented reality work principles. Let's start some statistic from Statista. With the augmented reality market valuing at $9.5 billion and growing, this is an incredibly important segment to take advantage to remain competitive in AR technologies application for an audience of 810 million active AR users on mobile. Augmented reality adds digital content onto a live camera feed, making that digital content look as if it is part of the physical world around you. In practice, this could be anything from making your face look like a dog to overlaying digital directions onto the physical screens around you. Augmented reality can let you see how furniture would look in your living room or play a digital board game on a box, for example. All these examples require understanding the physical world from the camera feed. The AR system must understand what is where in the world before adding relevant digital content at the right place. This is achieved using computer vision, which is what differentiates AR from VR, where users get transported into completely digital worlds. So, now that you know the meaning of AR and how does it work? First, computer vision understands what is in the world around the user from the content of the camera feed. This allows it to show digital content relevant to what the user is looking at. This digital content is then displayed in a realistic way so that it looks part of the real world. This is called rendering. Before breaking this down into more detail, let's use a concentrate example to make this clearer. Consider playing an augmented reality board game using a real carrier box as the physical support like in this figure. First, computer vision processes the raw image from the camera and recognizes the serial box. This triggers the game. The rendering module augments the original frame with the AR game, making sure it precisely overlaps with the Kirill box. For this, it uses the 3D position and orientation of the box determined by computer vision. Since augmented reality is live, it above has to happen every time a new frame comes from the camera. Most modern phones work at 30 frames per second, which gives us only 13 milliseconds to do all this. In many cases, AR feed you see throughout the camera is delayed by roughly 50 milliseconds to allow to this happen, but our brain does not notice. And why does AR need computer vision? While our brain is extremely good at understanding the images, this remains a very difficult problem for computers. There is a whole branch of computer science dedicated to it called computer vision. Augmented reality requires understanding the world around the user in terms of both semantic and 3D geometry. Semantics answer the what question. For example, recognizing serial box or that there is a face in the image. Geometry answers the where question and infers where the serial box or the face are in the 3D world and which way they are facing. Without geometry, AR content cannot be displayed at the right place and angle, which is essential to make it feel of the physical world. Often we need to develop new techniques for each domain. For example, computer vision methods that work as serial box are quite different from those used for a face. Semantic and geometry of the world. Traditionally, computer vision techniques used for understanding these two aspects are quite different. On the semantic side, we have seen much progress thanks to deep learning, which typically figures out what is an image without worrying about 3D geometry. On its own, it enables basic form of AR. For example, whenever computer vision recognized an object, we could display relevant information floating on the screen, but it will not work, not look enter the physical object. To do this would require the geometric side of computer vision, which builds of concepts from projective geometry. In the serial box example, we need to know its position and orientation with respect to camera to enter the AR game correctly when we display it. How does AR display digital content? For each augmented reality experience, we need to define some logic beforehand. This specifies which digital content to trigger when something is recognized. In the live AR system, upon recognition, the rendering module displays the relevant content onto the camera feed, the last step in the AR pipeline. Making this fast and realistic is very challenging, particularly for wearable devices like glasses. And another way to explain to how AR works is to consider computer vision as inverse rendering. Intuitively, computer vision recognizes and understands the 3D world from the 2D image. So that we can add digital content that is then rendered onto the 2D font screen. AR is very active field, and in the future we expect to see many exciting developments. As computer vision gets better at understanding the world around us, AR experience will more immersive and exciting. Moreover, augmented reality today lives mostly on smartphones, but it can happen on any device with a camera. When enough computational power will be able on AR glasses, we expect this medium to make AR mainstream, enhancing the way we live, work, shop, and play. And the basic process of augmented reality work can be divided into three steps: input, processing, and reflection. Reflection or output, it's the same. Input: one or more sensors capture information from the real world. Uh, we can say that, and also data collection from the real world. Processing units interprets the data acquired through different hardware and software resources. And output or reflection, it displays the user both information providing the feeling that virtual objects are part of the real world. Different types of sensor that respond to physical or chemical stimuli from real environment and provide the necessary data for the development of the system. The creation of any AI elements requires precise capturing of the real-world objects to augment them realistically on your display. For this purpose, a variety of sensors has been adopted in the AR software, such as mechanical, biological, acoustic, optical, and environmental ones. Mechanical sensors capture the object's position, acceleration, shape, mass, and displacement. Their common areas of application include the determination of the object's position, weight, and movements. Biological sensors measure the object's heart rate, temperature, neural activity, and respiration rate. They are applicable in the area of mood identification as well as the evaluation of mental and physical states of people. Acoustic sensors provide accurate data on the sound's volume, frequency, phase, and modulations, which is highly reliable in the terms of sound detection and speech recognition. Optimal sensors report data on the object's emissive, refraction, light wave frequency, brightness, and luminance, which is handled terms of computer vision detection, presence detection, and IR motion analysis. And environmental sensors provide data on temperature and humidity of the surround every moment. One of the critical tools to build fascinating air experience is the deep sensing camera, a camera that captures 3D images. AR devices traditionally have at least one camera, while some of them have two for deep sensing. It's also common to install IR camera in the device to allow heat mapping and advanced deep sensing. And output. The devices for displaying the information can be divided into variable and non-variable devices. Variable devices are AR smart glasses, AR contact lenses, and etc. Non-variable devices are smartphones, tablets, and PC, and etc. Optical see-through display. Optical see-through display, the virtual contents are projected onto the interface to mix with the real skin optically. For example, HoloLens and Moverio. Video see-through display. Video see-through display has two work modalities. One uses HMD devices and the other works with the camera and screen in handheld devices. For example, smartphones and tablets. And there is also software part. The primary function of software components is to interpret data in order to alter and enhance it. High level. Currently, various software development kit tools, including as Euphoria, ARKit, ARCore, Wigtooth, AR Toolkit, Easy AR, and Lay AR, assist in the development of applications. Programming libraries, computer vision, image processing, and HCI are examples of low-level fields that change depending on the application or developer's demands. And types of augmented reality. Augmented reality app development can take a number of forms depending on the business goals you are pursuing with your application. Let's take a look at the main types of AR solution. Marker-based augmented reality, location-based augmented reality, projection augmented reality, superimposition-based augmented reality. Marker-based augmented reality. This type of AR application is based on image recognition or image makers. Once the application detects an image or object that it can recognize, it overlays digital information on the maker. Such solution can use 3D or non-3D objects such as QR codes as markers. These are examples. Markerless augmented reality or location-based augmented reality. Location-based augmented reality solutions are mostly widely used implementation of augmented reality. Instead of using markers such as use GPS, acceleration compasses, and other location detectors to create air objects based on the current location. Pokemon Go is a great example of this type of application. Projection-based augmented reality. Application of this type rely on visual audiometry. They use complex algorithms and collect data from multiple sensors to identify objects' precise location and performs respective action. Projection AR can be used as a part of the car parking system since it can show hidden objects from built-in cameras. Architects and engineers can also use this technology to better study the environment for placing constructions. And superposition based AR. Applications really on superimposition are used in healthcare and medicine. The technology is self explaining. A real image of the environment is processed, recognized, and overlaid with the AR object.